In the 1800s, physicists had a big problem. Two, in fact. One of the problems is that physicists couldn't understand how light moved. They eventually figured this out with special relativity, made by Einstein in 1905. The other problem was that the wave theory of light, the theory that had let scientists understand the way light worked, the way light diffracted, the way light refracted, failed when it came to blackbody radiation. It was wondered whether light was a particle or a wave. At the first, Newton thought that light was a particle, and therefore he thought that light hit in discrete chunks. But eventually it turned out that light was a wave, or at least that's what people thought with Young's double-slit experiment. Because what Young did is he took two slits, he fired light through it, and found that the light interfered, which meant that there was no other option but to say that light was a wave. And that's what physicists thought for the next 100, 200 years. And that's when quantum mechanics came along, told them different. Einstein then came up with his photoelectric effect in 1905, where he noticed that there was an equation that could explain why certain frequencies of light, high frequencies of light, seemed to emit electrons from metal. The only way this could be explained is if light actually did hit the screen in discrete chunks. If the light hit in waves, then the light would spread all of its energy across the metal, and therefore no electrons would be emitted straight away or after a very long period of time. But if the light came in discrete chunks, which eventually came to be known as photons, then the electrons could be emitted straight away, because all of the energy would hit an electron and emit it. But then we had a problem, because then we had a model of light which explained stuff like refraction, diffraction, the wave model of light, and then we had the particle theory of light, which explained why the photoelectric effect happened. So which one was right? So you may be asking, I'm pretty sure that I see light in waves. I've never seen individual particles of light. How come light hits in particles? I never see particles. Surely you'd see the light hitting in discrete chunks, like apparently they do. Well, the thing is they actually do, but the problem is the energy of a photon, hf, shows that the energy is related to Planck's constant. And Planck's constant is very, very small, equal to about 6 times 10 to the minus 34, which means that for any slightly intense amount of light, there is a huge number of photons. For example, if we look towards the sun, if we were to look towards the sun, then there would be about 20 million billion photons coming towards the sun into my eye every second, because the energy of each individual photon is so tiny that there is a huge number of photons entering my eye every second, even though the sun is 150 million kilometers away, and even though my eye is very, very small. So that just goes to show why we see light seem to act like a wave. It's because the number of photons are so massive that it seems very continuous, and our eyes don't have the resolution to pick out the individual photons. In reality, when any light hits a desk, hits a wall, hits anything, there are actually individual pieces of light, photons, hitting the surface, but because there's so many of them, you just can't see them. So now let's come up with some analogies in real life to see what quantum mechanics would be like if it was on this scale. Let's just take the water over here. I'm going to throw the stick in it, and let's just see what happens. You can see that it makes little ripples in the water. And if we were to work out that with classical mechanics, we could work out from the depth of the waves, from the speed of the waves, we could work out how much energy was spread out by that wave and how much energy it would hit in certain locations. In quantum mechanics, what it tells you is that all of that energy, when it hits the shore, would be put into one single point. And it turns out that if you do the maths and you work out how much power, how much oomph the impact has if it hits a single atom, like in quantum mechanics, the power and the force in that one atom is the same as the power of a car. So as you can see, when you go right down to the very small, stuff seems to act very, very weirdly. In 1924, Louis de Broglie, in his PhD, theorized what would change quantum mechanics and our description of nature forever. He found, using relations such as E equals hf for a photon, E equals mc squared for particles, C equals lambda f, and other stuff like that, that P is equal to h over lambda, i.e. momentum is equal to Planck's constant divided by the wavelength of the particle. Now what this meant is that particles had a wavelength, and waves had a momentum. So particles could be like waves, and waves could be like particles. So what's going on there? Well, it's the start of what is now known as wave-particle duality. It's the fact that we can describe anything, particles, waves, light, electrons, photons, as both waves and particles at the same time. Now this confused many physicists, but using quantum mechanics, you can explain where that wave-like nature for anything that we thought was like particles comes about. In 1927, two physicists accidentally left their X-ray diffraction setup left on. When they came back after many hours, they found the laser still on and they realised that their crystal had melted. But when it reformed, it had a perfect lattice, which meant that it was a perfect microscopic diffraction grating, sort of like a double-slit experiment, but with more slits. When they fired electrons through it, they found something incredible. They turned the electron beam on with their fluorescent coating, and they found that the electrons, once the setup turned on, actually showed wave-like properties. It had a wavelength associated with it, which immediately showed that de Broglie's theory of particle-wave duality was correct. Let's say I had a coin, and I flipped it. Now if this was a normal coin, I could ask you, what's the chance that the coin is heads? And you would say 50%. But surely the coin's already landed. Surely the coin is either definitely 100% heads or 0% heads. It's already landed. It's just your knowledge of what's going on. You think that it's 50%, but in reality it isn't. However, that's not how the quantum world works. In reality, the coin itself doesn't know if it's heads or tails. Before it's observed, it could be either heads or tails, and it's effectively both. It's in a mixed state of being both heads and tails until I open my hand up and it's heads or tails. And only before an observation has occurred do the quantum effects happen. If anything is observed in a quantum experiment, all of the quantum natures disappear, all of the probabilistic wave-like characteristics of particles disappear, and everything turns back to normal. So just by looking at quantum objects, they seem to know that you're looking at them. And that's one of the strangest things about quantum mechanics. The world knows that it's being watched. One aspect of wave-particle duality that this analogy shows us is that we don't know about where the particle is until we look. From the uncertainty principle that I was explaining earlier, we can see that the standard deviation in position times the standard deviation in momentum has to always be bigger than Planck's constant divided by 4 pi. Now that means that if we know exactly what the momentum of a particle is, then the standard deviation is 0, because we know exactly what it is, therefore there's no deviation, no second guess at what the momentum really is. Then the position has an infinite possibility throughout all the space of being there, which means that the probability of finding the particle throughout the entire universe is equal, because the standard deviation is infinite. We don't know where it is at all. So if we just take any position on this graph, x, and plot the probability of finding the particle at x, you can see that it creates a flat line. But as we saw earlier, with the de Broglie wavelength, and with those experiments, everything has a wave-like nature as well, which means that if we were to plot a function which described the way that the particle interacted with the world, the way that we see it on those experiments, then we can see that it also has a wave-like nature. So it's going to have a wavy, sort of trigonometric curve. But standard functions don't go from a curve to a straight line by just squaring it. You have to square a wave function of a wave to find out the probability of finding something at that point. But as you can see, our standard functions of sine, cosine are not going to be able to be squared to a flat line. So physicists only had one option. They had to start using complex powers of E, which is where everything starts to get a bit abstract. Because A is the probability of finding the particle, theta is the angle, and E is just E, the number E, which is about 2.7, and it turns out that E to the I theta goes all the way around the complex plane, and A will never change, which means that we now have an oscillating pattern, but we have a magnitude that stays the same. And the equation that seemed to do it for physicists was that the wave function is equal to this number A times e to the power of 2 pi IPX over Planck's constant. Now I don't really understand myself what this means, but this is how we understand quantum mechanics, and this is how we understand the way that particles interact, how they move through space, and how they move through time. And as you can see, we're having to start using imaginary numbers, imaginary concepts, to explain reality. And that's just how strange quantum mechanics is. So, quantum mechanics, a theory based entirely off of chance.
As we've seen, we started with the wave-like model of light, which physicists thought was right for 100 years. Then came along Einstein, in his miraculous year of 1905, came up with both special relativity and the photoelectric effect, showing that light was in fact made of particles. And then de Broglie came along, told us that particles were waves, and waves of light were also particles, and both waves and particles were merged into one in a wave-particle duality. And then Schrödinger, with his theory of his wave function, showed that imaginary numbers were what were needed to explain the strange nature of these particles and waves, and just shows how strange the subject really is. So still, after 100 years of equations and theories by some of the best physicists in the world, we still don't really understand what quantum mechanics is. Do you?
Take two. We can see from the uncertainty principle that I was explaining earlier that the standard deviation of position, delta x.
Go.
What are you doing? Okay. E equals h lambda, E equals doesn't equal h lambda. Means that A is the same everywhere, la la la. Stuff seems to act very, very weirdly.
Take 6.
Okay, let's take this seriously, okay?